Hi class, welcome to our first lecture. For the remote segment of multivariate calculus. So the rest of the semester, format-wise, is going to be very similar to what we had been following in in-person lectures. So ideally, you would have already submitted your quiz that's going to be due on March 30th by midnight before starting this portion of the lectures. And so following format, we're going to have an abbreviated lecture, and this lecture is going to be an introduction to how to find critical points for functions of two variables. So let's get started, and I'm going to shift the screen over here, and let's remove my face since I'll be looking down at my notes. Here we go, maybe. Let's pause it for all right, well, it looks like I won't be able to get rid of my face at this time, so let us keep going. All right, so we are going to be trying to find critical points of a function of two variables. And so today we'll be learning how to find local extrema and saddle points. So if you think all the way back to Calculus 1, think about how you would have tried to find a critical point for a single variable function. And remember, to find the critical point for a single variable function, you have to take the first derivative, and wherever the first derivative is 0 or not defined, you have your critical point. So similarly, dealing with functions of two variables, critical points, bear with me, this is my first time with this setup. So critical points are where the gradient of f is equal to 0 or is undefined. All right, now feel free to take notes along with me, which is why I'm writing it out so you can keep up as far as pace, although my pace is probably quite slower than yours at this point. I will get neater and faster with time. But also, I have posted the lecture notes to Moodle from last semester's course, so feel free to look on those as well. All right, so now to find critical points, we need to set the gradient of our multivariable function equal to 0, right? We need to figure out where that is 0, and then we also need to figure out where that is undefined. So in order to do that, we have a max, min, or saddle test that we run. So it's going to be a max, min, saddle test. Okay, so for that test, we are looking for something that we're going to call D, right? So D is going to be for our mixed partial derivatives. So D is equal to our second order partial derivative with respect to x, so of x with respect to x, times the second order partial derivative of y with respect to y, minus the second order mixed partial, f with respect to x, then with respect to y, squared, and we evaluate D at the point. Okay, so this is very important, so I'm going to make it red. The test is when D is greater than 0, and this D is really the determinant of our function. So when D is greater than 0, we have a max or a min. So a local max or a local min. We'll talk about global maxes and mins next time. All right, but D just being positive doesn't tell you whether it's a max or a min. We have to do a concavity test. And if you can remember back all the way to last lecture, we started to talk about that in reference to second order partial derivatives. So we have a max if our second order partial is less than 0. Okay, so that is going to be concave down. So we're just looking here at the second order with respect to x for consistency. You could look at y as well, because this would be concave down if we're less than 0. Okay, and if we're going to have a min, if we're greater than 0. Just erase that. Because that means we are concave up, and I'm going to write it over here. We'll insert that there. Okay, now unfortunately I have to add a new page here to keep going. Okay, so if D is greater than 0, we have a min or a max, then we have to look at the second order partial with respect to likes, so either XX or X or YY, and if that's less than 0, we're concave down, so we have a max. If we are greater than 0, we're concave up, so we have a min. So if D comes out to less than 0, we have a saddle point. And a saddle point is exactly what it sounds like. So think about a saddle, and it kind of goes down or up. It's like a little curvy, so it's not going to be a max or min. It's going to be like an inflection point where you're changing slope. All right. And if D is equal to 0, we have to determine by hand whether it's a max, min, or saddle, and we do some trial and error for that. Basically, we plug in some points and see what happens. All right, so this is going to be determined by hand. And unfortunately, since you're not able to ask me questions in real time during these lectures, I'll have a forum that you can post on in each week's content, and I will check it regularly. And I can get back to you. We'll figure out if we want to do some kind of Google Hangout meeting for office hours or that kind of thing to address any questions that you have. So we'll take that one case at a time at this point. All right, so let us start with an exercise. So it's going to be exercise 20.1. So we're going to find the critical points. Okay, for the following function. So f of x and y is equal to minus 4x squared plus x squared y squared plus y cubed minus 9y. All right, so remember we have to start by finding where the gradient is 0 or undefined. So our first step is to find the gradient, so we need to take the first order partial derivatives, first with respect to x and then with respect to y. So f sub x, okay, is going to be minus 8x, okay, plus, and we have x squared, y squared, so that's going to become 2x, y squared. And then all the rest are just y, so it's treated as a constant, so we're okay there. Okay, and then we have, with respect to y, is going to be, all right, so now we have 2x squared y plus 3y squared minus 9. Okay, so now we have our I hat and j hat components of the gradient. So this is really the trickiest part of finding critical points. We need to determine where we have x or y equal to 0 or undefined. So we have to figure out where our gradient is 0 or undefined. So we have to do lots of factoring. All right, so we have to be very careful with our factoring that we don't oversimplify and lose our roots. So let's begin with, so what we're going to do is we are going to start by finding the roots of our derivative with respect to y, and with respect to x. And it doesn't matter which order to do this, you do this in, just be strategic. So start with, I would recommend, the component that is most easily factorable. So let's start by finding the roots of our x component. So here we have our minus 8x plus 2xy squared, and we set the partial derivative equal to 0. All right, so here we can definitely factor out a 2x. And so then we're left with minus 4 plus y squared in the parentheses, and that is equal to 0. So our roots here are that we have to investigate when 2x is equal to 0 or x equal to 0. And also we have to investigate when y squared minus 4 is equal to 0, so y squared equal to 4. And so that tells us we need to look at y equal to 2 or y equal to minus 2. Okay, so here we have 3 values that we are going to investigate further. All right, so I'm going to open up a new sheet to take a look at this. Now, what we're going to do is we're going to take these values for x and y, and we're going to plug them in to our partial with respect to y, our y component of our gradient, and set that equal to 0 to find the roots. All right, so let's do it. Okay, so first we had x equal to 0. And we are going ahead and we're going to plug that into our partial with respect to y. So remember, I'm just going to write it up above so we can refer to it. Our partial with respect to y was 2x squared y plus 3y squared minus 9. Okay, so we set that equal to 0. All right, so first we are going to plug into that partial with respect to y. We're going to plug in x is equal to 0. And so if we plug in x is equal to 0, we end up with 3y squared minus 9 is equal to 0. All right, so we can solve that and we find a critical point or value for y at y squared equals 3. And so that tells us that y is equal to plus or minus the square root of 3. So that is our value of y when x equals 0. So we just found our first 2 potential critical points. Okay, so this gives us a critical point of x equal to 0 and y equal to positive the square root of 3. And also, when x equals 0, we have to look at y equal minus the square root of 3. All right, so that is our first two, those are our first 2 critical points that we're going to investigate further. And so next, let us look at what happens when y is equal to 2. Okay, so when we plug in a value for y into our y component of our gradient, it's going to give us a value for x back, and then we'll get another critical point. Okay, so let's try it. Now here we are going to have, so y is 2, so we have 4x squared plus, so 2 squared is 4 times 3 is 12 minus 9, and we have to set that equal to 0. So we end up with 4x squared is equal to minus 3. Uh-oh. All right, so you'll notice here that we have x squared equal to minus 3/4. So that's going to give us an imaginary number. So really, we have no solution here. So this doesn't get us any further. So let's move on. Okay, no critical point there. So I'm just going to open up a new sheet again. All right, so next, let's look at our last one. Let's look at y is equal to minus 2. And if we go ahead and we plug that in, we end up with minus 4x squared plus 12 minus 9 is 0. And so this gives us 4x squared is equal to 3. So x is equal to plus or minus the square root of 3/2. Okay, so once again, we get 2 critical points out of this value for y. So we end up with, we have x is positive the square root of 3/2, and y is minus 2. And we also have minus the square root of 3/2 for x, and we have that's when y is minus 2. So now we have 4 critical points to investigate further. And so now we have to do the second order test to determine whether or not these points give us a local min, local max, or saddle. So let's do our test. Bear with me 1 second. Okay, so for our test, remember it was D is equal to second order with respect to x times the second order with respect to y minus the mixed second order squared. Okay, so that means we need to take our second order partial derivatives now. So remember that our first partial with respect to x was minus 8x plus 2xy squared. And our first order partial with respect to y was 2x squared y plus 3y squared minus 9. Okay, so now we need, let's take the second order with respect to x. So that's going to be minus 8, okay, plus 2y squared. And then our second order with respect to y is going to be 2x squared plus 6y. Okay, and then our mixed is just going to be 4xy. Sorry about pausing there for a second. I just had a bit of a brain cramp and I was looking at the second order partial instead of the first. So now looking at the first order partial with respect to x and taking the second order partial derivative with respect to y. All right. So now with respect to y, that's going to be 4xy. All right. So now we have all our partials and we just need to plug it in now to our formula for D. And so let's start a new page for that. So D, I'm just going to write it up here, is going to be equal to minus 8 plus 2y squared. Okay, so I just inserted my second order partial with respect to x there. Okay, and then we have 2x squared plus 6y, so that's my second order with respect to y. And then we're going to subtract off our mixed second order, which was minus 4, so which was 4xy squared. 4xy, and then we square it. Okay, so now we just need to plug in our critical points into D. So D, evaluated at 0, x equals 0, and y equals the square root of 3, is going to be minus 8 plus 6 times 6 times the square root of 3. Okay, so we're just plugging in. And that is going to be equal to minus 12 times the square root of 3. Okay, so that's clearly less than 0. And so we have a saddle point at 0 root 3. Okay, next, let's plug in 0 and minus the square root of 3. And that is going to be minus 8 plus 6 times minus 6 times the square root of 3. And that is going to equal 12 times the square root of 3. And so there, that's a positive. And so we have a max or a min. So to determine whether it's a max or a min, we have to look at the concavity. Okay, so looking at here, this is our f, our second order with respect to x, or we could look at our second order with respect to y. Either one would work fine. And so this is going to be minus 8 plus 6, which is minus 2. All right. And so there we have concave down. Okay. So we have concave down because we're negative. And if we're concave down, this is in the x direction, we are going to have a max. All right, so 0 minus 3 is going to be a max. Okay, and now we have 2 more points to look at. It's quite a process here, I know. Okay, so now we're looking at the square root of 3 over 2, and let's see, look at when y is minus 2. Okay, and so this is going to give us minus 8 plus 8 times 3 over 2 minus 12 minus 16 times 3. And this is going to give us minus 48. Okay, which is less than 0. So we have a saddle point. All right. And finally, lastly, let's look at minus the square root of 3 over 2 and minus 2. And so that's going to be still minus 8 plus 8, giving us 0 there. And 0 times anything is, of course, 0. But we have 3 over 2 plus 12. And then we subtract off 16 times 3. And that's going to give us minus 48. Surprise, surprise. And that's less than 0. So we have another saddle point. So we have 3 saddle points and 1 local max. All right. So our solution would be that we have, our answer would be that we have saddle points for 0, the square root of 3, and square root of 3 over 2 and minus 2, and minus the square root of 3 over 2 and minus 2. Okay, so we have 3 saddle points, and we have local max at 0 and minus the square root of 3. All right, let's put a box around that. So now let's just look at a plot of this function in GeoGebra to see how everything looks to make sure that our answers make sense. So opening up GeoGebra. All right, so here we see a plot of our function. Okay, so here's our function. And I went ahead and I plotted our critical points on the function. So first, critical point A, that's going to be 0 and the square root, x equals 0, y equals the square root of 3. Okay. And for x equals 0, y equals the square root of 3, we have a saddle point. Okay, so there's a saddle. Okay, so you can see what that looks like from a few different angles there. So then next, this point B here is our local max. It's a little challenging to see, but you could see that as a high point right there. And if you look at points C and D, so that's when x is the square root of 3 and y is minus 2, and x is minus the square root of 3 and y is minus 2, we have saddle points. So those purple are saddles, and so the purple points are saddle points, and the green is the local max there. All right, so when you're working on your homework, it's always helpful, I think, to use the tools that you have to construct these plots, to check to make sure that your critical points make sense and to get used to what these different functions look like. So that is going to be all I have for you for this lecture, and I'll see you again very soon for lecture 21.